So now here is the first blow. Okay, first step towards interpreting these terms in the Taylor expansion of phi of omega. Phi of omega is made up of, as we go along, it has a phi 0, it has a phi 1, it has a phi 2. Okay, do we need to consider a phi 3? We'll see. Phi 0 was the absolute phase or the initial phase, phi 1 was group delay, and phi 2 is what we call group delay dispersion. Okay, so first and foremost, as I earlier mentioned, the absolute phase is the same, be it in the frequency or time domain, because it has no dependence of frequency or time whatsoever. It's, in that sense, a constant quantity. Okay, but what do we mean by the so-called absolute phase, and how do we even reference it, and so on and so forth, right? I'm going to show you a view graph of this, but it's a good idea to build some intuition about this before I give it away. Suppose I have a clock. So pardon my poor artistic skills. A clock which consists of a dial. If I think of this as a clock, you're instantly going to say, okay, this is 12 or 0, 1, 2, 3, 6, 9. Because we see clocks day in and day out, analog ones. We still see, yeah. Maybe a couple of generations down the line, a generation that's a lot more digital will probably never see an analog clock and not even recognize this. But on the other hand, suppose there's another dial. I told you that this dial is a compass, a mariner's compass. What is your first question going to be if I showed you such a dial and said, hey, this is a compass? Now will you confidently say, hey, look, this is a special point on my dial? Google Maps has something like this. Yeah. So here, what would be the first question we ask? Where's the north? So where's the reference? What is north? The reference or the zero. Okay, you measure the absolute phase, the zeroth order phase as we are calling. But where's the zero of the scale? If I have no idea of that, or no robust and consistent definition of that, any measurement that I proclaim is either meaningless or it's subjective, like my favorite flavor of ice cream. It's only as significant as that, right? So we ought to have a robust definition of a reference for this at all. This quantity is therefore not entirely unambiguous in its definition or choice. Ergo, therefore, we need to define what we are measuring very well. You will hear statements like absolute phases have no meaning in optics. Such uh, dictums are also written about or spoken about even in formal literature. It is for this reason that referencing them is, is not an absolute, uh, cannot be done in an absolute sense, right? Therefore, we need some reference to figure this out. Fortunately, or where it matters, fortunately, there is a reference. This quantity, the zeroth order phase, itself needs to be something that we even bother about, the zeroth order phase or the absolute phase, only in the case of pulses. If you had a wave that started, the cosmic microwave background radiation started to be emitted or whatever, and is going to go on for beyond our lifetimes uninterrupted, which would be magical for whatever it's worth, uh, then the absolute phase has very little or no meaning. The absolute phase has a reasonable meaning only when the pulse itself, or in scenarios where we can even count the number of cycles, or I would say something of the nature of a countable or trackable number of cycles, and I really need to keep track of this quantity, which varies from 0 to 2 pi within one cycle of the carrier wave. What do I mean? Consider the example of these two pulses which I have plotted. The pulse to the left is also a so-called ultra-short pulse. Now the zeroth order phase needs a reference point. With respect to what am I measuring the zeroth order phase? In the case of pulses, well-behaved pulses, the amplitude function, the envelope function, has a maximum. You see, how do I mark the zero of this time axis? This is the equivalent question we are asking. How do I mark the zero of time? Why should it be here, not here, not here, not here, or why not here at some tail? Who sponsored the zero to be at the maximum? Nobody. It seems to be like a matter of prejudice. However, the point being that if I consider and have an idealized Gaussian like pulse, or an idealized Gaussian pulse in my mind, there is a symmetry point in the shape of the envelope. There is a maximum on either side of it. An ideal Gaussian pulse with a flat phase, okay, is symmetric in time. Yes. So I can choose a point based on symmetry, which is inherent to the pulse. In other words, what are we seeking? We are seeking to self-reference stuff. Self-reference to things within the pulse itself, right? And then do measurements, because that's our only chance. Our best shot for measuring the shortest events made by humankind is a self-referenced way, right? I'm okay, a digression, but let me put it to be this. If historically a site was being excavated and we found objects on which there were inscriptions, how can we be sure that it is not just a portrait or a drawing versus it being a language? We only have few alphabets. Or a million years later, this civilization, say, were to become fossilized and somebody discovered something, maybe a piece of paper still survived or whatever, with a program written on it, right? They have no idea to know the meaning of these symbols. But then, based on just one piece, one ought to infer what this is about, right? This actually happens in the case of inscriptions in a tomb. There, one has to reference things either by themselves, or in the case of inscriptions in a tomb, one found the so-called Rosetta Stone, which connected uh, the carvings and inscriptions to a version of Greek. And since we knew Greek, ancient Greek, things could be translated, and you figured that it's a language. In other cases, it wasn't so trivial. For the case of the Indus civilization, one didn't really know if the symbols that were found there constituted a language, and one had to use self-referencing techniques to figure this out, whether it constituted a language. And in that case, entropy, a measure of disorder, became a key variable. So likewise here, when we have these pulses, which are sort of unique and don't submit themselves to any other man-made reference, we need a reference within the thing we are about to discover itself, even before we discover it. Okay, SETI, think about it, extraterrestrial or aliens project, as we call it, search for extraterrestrial intelligence. If we have a signal from somewhere outside in the cosmos, how do we know that this is a robust signal from an alien civilization? We have no clue, right? We are not going to be able to find the source and ask, did you send this signal? We have to figure out by means, some other means, whether this constitutes a useful signal or not, right? So again, their self-referencing is the only goal. Here, it's we created this problem for ourselves, and we have got to determine it. Or as one of the pioneers in this field, Wayne Knox, says, if you haven't measured it, you haven't made it. You don't even know if you made a short pulse. So that is really, the message is clear, that it has to be self-referenced. Fortunately for these well-behaved pulses, if they are Gaussian or close to Gaussian, there and thereabouts, waveforms that deviate from a Gaussian, yet I have a reference point, it is close to a Gaussian or a secant hyperbolic. We will later see why we are so biased towards these functions, actually even a Gaussian, right? The Gaussian has statistical reasons, but for laser pulses, secant hyperbolic is also an important form of the pulse. For those of you who are familiar with the word solitons, this may ring a bell. But the point being that these are nonetheless, and our catchphrase is well-behaved pulses. If they are well-behaved, then the envelope is of this kind, and I can essentially pick a point, the most symmetric point of the envelope to be my reference point, and mark my zero of time over there. And this definition, the good thing is, it is going to be consistent across pulses produced by laser 1, laser 2, laser 3, lasers in India, in Europe, in US, in Japan. If they are good lasers, then they will all produce such pulses which are well behaved, and all these pulses have a maximum in the amplitude, which I have the hope of measuring in some domain, and in the time domain, if I pick that maximal point, I can have a robust definition of the zero of the scale. So zero is the most important number in the numeric system, or the number line too. So also here we are figuring out the zero, and there the zeroth order or the absolute phase is going to be something of significance. Now, if I even consider the so-called 4-cycle pulse, what do I mean by the 4-cycle pulse? Where are the 4 cycles? The 4 cycles are essentially the number of cycles right under the full width at half maximum, which is a measure which we had for these pulses, right? You remember? We wrote down a Gaussian pulse. We defined a Gaussian pulse as e to the minus t square divided by tau half width at 1 over e. This was 1 over e, and we related the half width at 1 over e to the full width. Okay, sorry about that. Full width at half max, which is visually easy to pick up. So the number of cycles 1, 2. So on either side of the maximum, we have about 2 cycles within this envelope. So this is a 4 cycle pulse. Here I have what we call a single cycle pulse. Here is a full width at half max. We have approximately just one cycle underneath the envelope. Single cycle pulse. Both are members of the same family. However, slim, short, ultra short, or not so ultra short they may be, it's challenging enough to produce 4 cycle pulses, but there are techniques well developed to produce these single cycle pulses. But the point that we are trying to make here is that this absolute phase or the zeroth order phase is a meaningful quantity, or a quantity, a sought after quantity, in the case of these few cycle pulses. The case of these few cycle pulses, and may or may not play such a big role if pulses were significantly longer than that. They become almost, uh, you know, things we can't ignore in the case of very short pulses. Why? Again, the argument I'm going to present now is fairly visual. We have plotted in this case, let me take these things away. We have plotted in this case 2 pulses, and please watch what I'm coloring now. The first pulse, which is the dark line, it has a maximum which coincides with the maximum of the envelope. Agree? And where is that point? Changing highlighter, the pen. The maximum of the envelope is also my 0 point. So the maximum of the carrier of the of this 0 shifted pulse matches that of the envelope here, right? So for this pulse I would immediately associate this with a cosine function. At the 0 of time, I have the maximum, the maximum of my cycle coincides. And among the trigonometric functions which I would use for describing the carrier, I would use cosine. Right here, phi of t is constant or 0. I can see that the carrier frequency is omega naught, and there is no variation in the instantaneous frequency visually. So this would be just a cosine omega naught t. Agreed? Contrast that with the next pulse, which I'm going to highlight. That's the dotted line. What is the feature of the dotted line? The feature of this dotted line is the fact that at t is equal to 0, there is a 0 crossing of the field. The field flips direction at the maximum of the envelope and has the value 0. So there is nothing at the maximum of the envelope. So this is more a sign, right? So whereas one of these pulses try to sketch this. has this sort of a field variation. Is it even visible? Sorry, bad choice of color. Try to keep it consistent, but so this is the form of the electric field underneath the envelope. The other guy is essentially this shape. So what is the key here? The key is shape of E, not U, right? Ankit. Shape of the electric field matters, ergo also the magnetic field, but the shape of the electric field matters for few cycle pulses. And that's the whole reason why this obsession with the so-called absolute phase. Zeroth order phase would actually be the more appropriate adjective and scientifically accurate terminology, but um, we will indeed see how this is measured. Now we got to ask, we are describing all this in the time domain, and in frequency domain, I said earlier, or I gave up the cause of time domain and said all the measurements we do will have to be measurements of the absolute value square of the electric field. The moment we make measurements of this type, we've lost phase information. So how are we going to retrieve any of these phases? So there I use another term that becomes of importance for us after self-referencing. Retrieval after self-referenced measurements are also going to play a key role. So the shape of the electric field is what the absolute phase quantifies for single, or here why just single, even for this pulse, the 4-cycle pulse. Now that we have a trained eye, we can absolutely see what's happening. I can distinguish between the black curve, which is in which the carrier wave defined through a cosinusoidal function, cosine of omega naught t, is unshifted with respect to the maximum, whereas there's a pi shift in the case of the other companion pulse, which is in the gray scale. So this is cosine omega naught t plus a constant factor of pi. And why is cosine now also sort of coming to us naturally? Because we had e to the I omega naught t plus some phi 0. Let's say the other terms are 0 in the Taylor expansion. We are all the while bothered only about the real part of this, which is cosine omega t plus phi naught, phi 0, the 0th order phase, right? So therefore, a sine, a pulse with a 0 crossing at the 0 of time, is essentially cosine omega naught t plus a shift of pi over okay, crosses 0 at t0, t is equal to 0. So all these and any in between value for phi naught, any other intermediate shape for these pulses are all captured by the single quantity, that is phi 0, shape of E underneath the envelope. Alright. Now I'm more or less out of time for today, but I'll leave you with a thought. In most measurements that we do, what we are actually measuring is as a function of the envelope or the absolute value square, or they are all irradiance measurements. The moment we measure irradiance, even if we could do a direct time measurement, that is measure everything in the time domain, do a chronoscopy, if the detector that we use responds to the absolute value square of E in time of frequency domain, we will get information about whatever measurement we are doing from the perspective of the envelope, not from the perspective of the carrier wave or the field. So therefore we must distinguish measurements from the perspective of being phenomena that are sensitive density variations, intensity, power, energy, versus sensitivity to the field that is underneath this envelope. In some sense, field is the real thing oscillating. Field only cares about the instantaneous frequency, of which carrier frequency is the centerpiece. If we therefore want to have anything that is field driven, can I think of a light field effect transistor, field driven transistor performing at petahertz frequencies? What would that mean? It would essentially mean doing things, manipulating things, measuring things, controlling things as fast as the field oscillates. If we do so, if we dream of doing so, or if we plan doing anything of that type, then a measure of our ability to do this, and probably a measure of field sensitivity or sensitiveness itself, would then correspond to, can I measure things as a function of the absolute phase? Can I do measurements and variations which are sensitive to the absolute phase? Since the absolute phase is essentially a difference between the maximum of the envelope and the maximum of the carrier. A sinusoidal wave has an absolute phase of pi over 2. What is pi over 2? It's the phase difference between envelope and the carrier. So therefore we maybe, going by our current definition for the absolute phase, maybe we should call this the carrier envelope phase, the relative phase difference between the carrier and envelope. So we will soon start calling the absolute phase the carrier envelope phase in the context of these pulses. Agreed? It's a very representative and reasonable name for this, right? So let's have this as the breakpoint for this interactional lecture. I know I've spent considerable time on this one slide, but that is the absolute phase or carrier envelope phase, and field sensitive measurements and field driven phenomena would characteristically show sensitivity to variations in the absolute phase. It is an entirely different matter how we are going to measure it. After measuring it, how we are going to control it. Control is not that challenging. It's, as you're going to see, fairly straightforward to vary this in a controlled way, whereas measuring this is actually a challenge. And I would invite you to start thinking about or devising methods for how would you measure the absolute phase in the case of few cycle pulses. What would be your strategy? I would like to hear about that, even in a say tutorial or discussion that we have when we meet next. Okay, so with that, I'm done for today. We can have a few minute discussion. I may have to uh, close otherwise for today. We can stop the recording.